So we're looking at the question, what are we being asked to solve for? We want grams of sodium. All right, what information are we given? We have 19.2 liters of chlorine gas. Do we have any other given information? Okay. I would say we have the balanced chemical. Is it balanced? They gave us numbers, so presumably it is balanced. A balanced chemical equation. Do we have any other given information? Say again? Yeah. They are giving us this expression that 1 mole of a gas has a volume of 22.4 liters for that gas. We could immediately make a substitution here. What's the gas that we're looking at? Chlorine. It's got to be chlorine gas, because we can determine that by looking at our chemical equation. The only thing that we actually see that's a gas would be the chlorine. We know it's a gas because it's got a G. Okay, the G from our chemical equation. So I want grams of sodium. I have a balanced chemical equation. I have this moles of chlorine equals 22.4 liters of chlorine. I'm actually going to add back that this has to be a gas. And then we also have 19.2 liters of chlorine. So what do we start with? Okay, so we go through and say I have grams of sodium in the numerator. It's a fine place to start. I don't know the grams of sodium, so I'm going to have to do a conversion. What do I want to do a conversion to? Okay, why do you want to write grams to moles? Okay, perfectly acceptable. Okay, we know we need grams for our final answer. If we look at all the given information has a lot of information about a different substance. The only way we're going to be able to deal with that substance conversion is if we're going through a chemical equation, and the units from our chemical equation is in moles. Okay, so if we're trying to start this out, we want grams of sodium. I know I have to do a conversion. Why not go to moles? Right, moles are kind of this universal unit, so hell with it, let's just go to it. Right, that's not a bad logic. Right? In fact, I would argue that's a perfectly acceptable, reasonable logic system. It doesn't mean it's the logic I would use, okay, but it's fine. Okay, so where do I find the conversion factor that relates grams to moles? That's on our periodic table. So we can go up to our periodic table since it is just sodium, right? Yeah. Okay, sodium is, depending on how precise you want to get, 22.99 grams per 1 mole. We now have a foothold in starting our problem, or starting our solve, because now we can go through and say, well, we have what we want. We have to get rid of the stuff that we don't want, which means we're going to have to do some other kind of calculation. And that other calculation, what do I know needs to be true? I need to get rid of the moles of sodium. Okay? So the moles of sodium would need to appear in the numerator. Okay? I don't know the actual moles of sodium, so I'm going to have to convert. So I have to relate the moles of sodium to something. Right? I can relate it to grams. I can relate it to pretty much anything I want. The question becomes, what is useful for me? So this is where having an idea of what other given information we've got can come in handy. If we go back and look at that given information, what might be useful for us to relate the sodium to? Chlorine. We got a ton of chlorine showing up in our given information. And we're running a calculation that has nothing to do with chlorine. So if I could somehow convert my moles of sodium into chlorine, that'd be pretty cool. All right? The unit that I would want to deal with, okay, could come to anything. Maybe I want to do grams of chlorine. So again, we'd ask, does that conversion factor exist? Is there a conversion factor that relates the mass of one substance to the moles of another substance? No, that's not one of our default conversions. Okay. What can we relate if we absolutely want to deal with the substance? Moles, a mole ratio. That mole ratio comes from the balanced chemical equation. So I can go back to my given information. They just gave it to me as the balanced chemical equation. They didn't actually tell me what things I wanted to relate to. So they're not intentionally, but they're not trying to give you all of the answers. They want you to try and think about and reason through what that given information is. Okay? So how many moles of sodium according to our balanced chemical equation? So we have to interpret from our equation. I'm looking for sodium. I see sodium over here, right? There's an Na. Should I be using that number? No, why not? That's not just sodium, that's sodium chloride. Okay, so again, what we're trying to do is find the thing that matches best as possible. The thing that matches best as possible is over on the reactant side. Okay, that's sodium all by itself. The number I'll use is the number directly in front of it. 2. Okay. I now need to figure out what number I have to associate with the chlorine, so I go to my chlorine. What's the number in front of it? It's an implied 1. What does this set me up with? Well, the moles of sodium now cancel. I didn't want those, so that's good. But now I have moles of chlorine. Did I want moles of chlorine? No. So what has to happen? I need to cancel it. Okay, so I have to run another conversion. In that other conversion, I want the moles of chlorine to cancel out. Do I know the moles of chlorine? Does any of my given information state the number of moles of chlorine? So, and again, this is where we're trying to be real careful with the language. Go, oh, well, it says 22.4. It doesn't say 22.4 moles. It says 22.4 liters is equal to a mole. So do I know the moles of chlorine? Okay. So, I know 1 mole of chlorine over 22.4. Answer my question. I'm important too. Do we know the moles of chlorine? No. It's not given information. I have to convert the moles of chlorine to something else. What something else do I want to convert to?
Liters.
Okay. Why do I want to convert to liters of chlorine? Okay. Going into moles of sodium wouldn't make any sense because that would undo it. Why not go into grams of chlorine? We don't have that. Really? We don't have the grams of chlorine related to the moles of chlorine?
It doesn't apply.
There we go. So what we're starting to move into isn't just a random let's throw stuff in there. It's a little bit of a chess match. You're not just moving your pawn. You're moving the pawn because you're predicting somebody else is going to do a different move so that you can move your knight. Okay? You have to project forwards what's happening. Okay? Particularly for a more advanced question. That's what these things are doing. You're trying to project the long game, not just do simple moves each time. Okay? So we'll go to moles of chlorine to liters of chlorine. Now we can pull the numbers from our given information. 1 mole of chlorine was 22.4 liters of chlorine. Depending on how you see decimal points, maybe you didn't see I put a decimal point, so I'll add 1 in there. Okay, what happens? The moles of chlorine cancel. I didn't want the moles of chlorine, so that's a good thing. Okay? But I brought in liters of chlorine. Do I want liters of chlorine? No, so what do I got to do? I need the liters of chlorine to cancel. So again, what I'll ask, do I have the liters of chlorine? Yes. Okay? Do you notice that what's happening in each and every single one of these solves, I'm asking the same style of question. Okay? Where do I want to start? Let's start with this. Why did I start with that? Because that's what I saw. Okay, move. Now that you've got a foothold, what do you do next? Well, I don't want that unit. So write that unit and the place where it cancels. Do I know that number? No. I need a conversion. What conversion do I use? Pick a conversion. That cancels one thing. That brings in another unit. Do I know that number? Every single time, it's the exact same question sequence. Okay? And I'm designing it that way to show you the flow so that every time we encounter a conversion question, that should be your flow process. That's why it's there. This means you don't have to memorize any formulas. What you have to memorize is what? The process. Cool. Is that it?
The intention behind what units you're using.
There it is. It's a process, and where do I find that information? That's your responsibility. Okay? The process, in theory, is starting to sink in, but theoretically, the process was addressed, taught, practiced in Unit 2. The only thing you should be working on is where do I find this information? That's it. Okay? Nobody trusts me. That's okay. I get it. I'm a scary person, and you didn't trust me back then, but now you're like, okay, maybe I got to trust you. Okay? You just made it a little bit more work, but now hopefully you're starting to recognize that process and no, we're doing the same thing each and every single time. We good? So now what do? Now we just punch numbers into a calculator and put it into active. Does that make sense? Okay, Logan, it looks like you're doing numbers. What was the number? 39.4 grams of sodium. Did anybody else run the number calculation as well? Okay, so we've got confirmation of that. This sets us up. It's now just a question of putting all that stuff in there. Okay. I'm going to backtrack out and complain a little bit about our active homework, or at least I may regret pushing that. Active sets it up so that you can put in all of this work. Okay? The intent is that you're not using active to solve it. You're using pencil and paper in your reasoning to solve it. Once you've got that done, now you take that work and you put it into active. That's the intent. If you're using active to solve it, you're doing it wrong. I don't care if you get the right answer, you're doing it wrong. Okay? Make sense? 39.4 is one of the numbers, so hey, could be right. Further questions on that one, or are we good? I'll take that to mean we're good. Okay. So the primary question that I would bet you're really asking about is kind of centered on that. What is an empirical formula? Okay, so I'm going to take a step away from that and say, I don't care about empirical, what is a formula? So if I asked what is a formula, does that work? Okay, we're going to get a couple different answers on that, which is good. This is why I picked it. We say, yes, that is absolutely a formula. The formula shows the elements that are in the compound. But you said no. Why'd you say no?
I did it before. I couldn't tell you how I did it, but I know for a fact something wrong.
Read the frickin' question.
Where is sodium?
Within the context of the question, is this a good formula? No. Does it say anything about potassium? No. Does it say anything about sodium in my formula? No. So in answering the question, that's a horrible formula. Okay? A better formula would be NaCO2. How about Na2CO3? Is that a formula? How about Na3C3O6? Is that a formula? Yeah. Right. So what do all of these things have in common? They all have sodium, carbon, and oxygen. So our formula has to contain the elements that are supposed to go into said compound. Right? That has to be true. What other information shows up? Right? And you used an interesting word there. You said the moles of each. Really? If I have a single molecule of NaCO2, how many moles of sodium do I have? I have a single molecule of that right there. How many moles of sodium are present? Okay, so some people are saying, what? Okay, let's try this. Equals moles of sodium, right? What am I starting with? One molecule of sodium, CO2, right? Just start with one of those. Okay, simple conversion, right? We just set this up.
The molecules isn't the same as
Fucking exact. Okay. What do I want? Well, I want moles to appear, and I want to get rid of my molecules, right? So can I convert molecules and moles?
Yes.
And maybe where you're stuttering is you're like, what's the substance? Which that's a good stutter. So let's lean into that a little bit, okay? Because we're trying to get rid of molecules of NaCO2, and I wanted moles of sodium. Do I have that conversion? No, I don't have that conversion because that's converting two things. I'm converting the measurement unit and the substance unit. I'm not allowed to do that. Okay? So what should we go through and convert? Measurement or substance? Measurement. So I want molecules of sodium CO2 to turn into moles of sodium CO2. Does that conversion factor exist? Yeah, that's the irritating conversion factor we never want to use. That was, just accept it. Okay? That's the 6.022 times 10 to the 23rd, which shows up where? Say again? With molecules. We wrote molecules on the bottom, so we'll go 6.022 times 10 to the 23rd. For those people that said 1, you should be kind of thinking a little harder now. Be like, but I was so confident. Okay? What happens? Molecules will cancel, and I've got moles of sodium CO2. I don't want moles of sodium CO2, so what has to happen? The moles of the sodium CO2 needs to cancel, and what needs to appear? The moles of the sodium, right? Because that's what I'm solving for. Where do I find the conversion factor to relate those? From a formula. How many times does sodium show up in NaCO2? Once. How many times does NaCO2 show up? Once. So now what can I go through and do? I run my calculation, right? Simple calculation. Okay. So how many moles of sodium appear in one molecule of sodium CO2? 1 over 6.022 times 10 to the 23rd. That sounds like a really small number of moles. Not 1. What are the units on the numbers in a chemical formula?
Molecules are present in this bond.
Okay, so we can go with how many molecules, okay, are related to the number of atoms that make it up. So there is 1 atom of sodium in 1 molecule of sodium CO2. Perfectly acceptable. You're allowed to do that. Do we like counting atoms and molecules? No, what did we do instead? We count moles instead, which means if I have 1 mole of sodium CO2, how many moles of sodium do I have? 1. All we're doing is interpreting the number associated with it. And we have to decide what unit we're going to attach to the number in the formula. If you want to use molecules, yes, molecules 100% works. Okay? Molecules as a unit sucks though, because that generally means we got to go back to Avogadro's number. Or we could go through and look at moles, in which case I don't have to deal with Avogadro's number and I can just be happy with the mole unit. I have Avogadro's number factored into this and I don't have to worry about it. So if I switch up the question and now say I want 1 mole of sodium and how many moles of sodium CO2, now it's 1 and 1. Now it makes sense. You have to track that mole to molecule conversion, okay? Which should sound really important because that is literally one of the questions off the practice exam, where we're talking about the value, moles versus molecules, and how the meaning changes slightly. Okay? So when I look at a chemical formula, I can decide it's molecules or moles. If we go all the way back to the question at hand, which unit do you want to choose it to be? I heard you say moles. Why do you want to choose it to be moles? It's not a bad answer, but I would argue you have a better answer for why you want to deal with moles. Read the question. It's given in moles. If I want to deal with molecules, what am I going to have to do? I have to convert all the moles into molecules. So why not just freaking start with moles? Yeah, go for it. So what would an empirical formula be? Sodium, the number next to it is now the number of moles that represent it. So how many moles represent sodium? 1.06. And how many moles represent our carbon? 0.528. How many moles represent our oxygen? 1.59. And ta-da, what do we have? We have a formula. Okay? That's literally what this is. This is now a formula. Okay? But remember, the whole point of our formula is not just moles, but also molecules. Okay? So that I can count the atoms that are present. Can I have 1.06 atoms of sodium? No. Now we've got a problem. So while this may represent a chemical formula, this will only function with the units of moles, and it does nothing for the units of molecules. So I want to alter how I present this formula to ensure that I get whole numbers. How can I ensure that I get whole numbers? Just rounding. Rounding makes whole numbers. Okay, cool. Try rounding it, and you get the answer wrong. So rounding doesn't work. How else can you get whole numbers?
Multiply them by the same.
So close. By the same is good. Divide them. Divide them by the smallest number you see. Because what's 0.528 divided by 0.528? 1. Is 1 a whole number? Ooh, that gets me a third of the way there. How about what happens when I take 1.59 and divide by 0.528? Right around 3. It gets darn close to 3. What happens when I take 1.06 and divide by 0.528? That gets darn close to 2. That's supposed to say 528. And when I do that division, sodium 2, carbon 1, oxygen, you said 3? Okay, and we now have a formula. But to get this formula, I had to reduce the numbers that were already there. Okay? I had to do that division. That division is ultimately now telling me the ratio of sodium to carbon to oxygen. Technically the sodium to carbon, the carbon to carbon, and the oxygen to carbon. Okay? It tells me a conversion factor. What the hell did a chemical formula tell me to begin with? Motherfucking conversion factor. Ta-da, there it all is. But this conversion factor now sets me up with whole numbers, and now it looks pretty. Okay? And now when I try and apply the molecule unit to my formula, it makes sense. Can I have 2 sodiums? 2 sodium atoms? Yeah. Can I have 1 carbon atom? Yeah. Okay? So what I've done is taken this convoluted count of a massive number of molecules, and I turned it into a ratio to give me this. This ratio is ultimately the reduced ratio, fully reduced. Right? Because we could have more. I could have had the formula Na4C2O6. Right? Does that still match the data that I've got? Actually, yeah, 100%. Because if I have Na4C2O6, what could I do? Divide everything by the smallest number. That would be the 2, and I would get Na2C1O3. Ta-da! Okay, so what the empirical formula does, by nature of how we calculate is it gives us the reduced ratio, the smallest possible whole numbers that we can put together to make up the compound. Okay? That's the empirical formula. Okay? Is this valuable information? 100 years ago? Yeah, it's awesome. Like now? No, it's fucking useless. Okay? Having this information gives us some information about what makes up the compound, but we have really fancy techniques and technologies that allow us to get a whole hell of a lot more information out of it without having to drill into a freaking empirical formula. Okay? So really the only reason we're having you do an empirical formula is for you to recognize that the numbers in there can be molecules or moles. That's it. That's the point of the empirical formula. Okay? Why does the empirical formula hold value? Because it tells us some information. That's about it. It tells us the ratio of the atoms present. So if I look at a really fancy compound, I'll make it even more complex. That's when I should pause the lecture video so at least the video goes faster. What would my formula be? What elements are present? Try that first. Okay. Carbon and hydrogen. How many carbons are there?
6.
How many hydrogens are there? 12. That is now a proper molecular formula. Is that an empirical formula? The empirical formula is the reduced ratio. Can I make that smaller? Yes. Okay, I could divide both numbers by the smallest number being 6, and that would take me to the formula C1H2. The C1H2 becomes my empirical formula. Why would we ever do that? We're now removing information, right? If I look at C1H2, does that look like that compound? Not at all. There's 6 frickin' carbons there. That makes no sense. The empirical formula is ultimately coming from how we discovered these elements and how we discover what elements are in them. We take a giant sample of that compound, we run a bunch of chemical reactions. The chemical reactions go through and say we have 20 grams of carbon and 15 grams of hydrogen, for lack of better numbers. Don't count it back to that. Okay? So we have those mass numbers. What can we do with those mass numbers? We can convert them into moles. Once we convert them into moles, we can now convert it into an empirical formula. But because we tore apart and exploded those individual molecules, and we have no idea how many molecules were in it, we have no idea what the actual composition is. We just know the ratio of the pieces that came out. Okay? You can do the same thing with speed traps, or not speed traps. Have you ever seen strips across the road, like 2 wires running across the road? Do you ever wonder what they're doing with those? They're tracking speed. Right? What they're trying to decide is, do we need to change the speed limit? Or maybe do we need to tell the police to come out and monitor this part of the road because people are speeding? Why? What do? They start a timer when something hits the first wire, and then they stop the timer when something hits the next wire. Okay? Based off the number of times, if we look at a car has 2 sets of wheels, right? Okay? You can then calculate the speed that someone was going through based off of how many times it gets pressed. Okay? It creates a ratio. And if they find out the average speed of people moving through there is 65 when it's supposed to be a 30, okay? 2 things could potentially happen. 1, they call the cops, hey, you need to come out here and monitor this street because people are going too fast. Or they go back to it and say, maybe that shouldn't be a speed limit of 35. Maybe it needs to be a speed limit of 60. Generally, they don't do that, but usually just send the cops. Okay? But that's the point of those things. They're taking an average to get an idea of what's going on. The empirical formula is an average. That's it. It gets us some information, but it's not perfect. Okay? Because what if the vehicle driving by doesn't have just 2 axles, it has 3 axles? Is that going to mess with the calculations? What if it's a freaking unicycle? Right? You want to really mess with it, get a fast unicycle and start driving over those back and forth. Like, what the hell is going on here? Right? It gets us some information enough that we can start thinking about to manipulate. So all we're trying to do with an empirical formula is figure out what that reduced ratio is. Bottom line. Right? That ratio is on units of either molecules or moles. We have to have the ability to do both, which is why we don't see decimals show up in our formulas, because we can't have fractional molecules. We can have fractional moles. Right? So if you're being asked to solve for an empirical formula, what do you have to go through and do? You have to determine the amount of moles that you were given and just associate that with each element. Which answer choice matches that? Ah, dang, I didn't reduce the ratio. Divide by the smallest number. Ta-da! There it is. That's it. That's all you got to do. All right? This one was straightforward because we gave you moles. Did we have to give you a measurement of moles? No. What else could we have given you a measurement of? Let's see. Is the next question going to be useful? Oh, next question is brutal. They went through and they give you a percent. Oh, seriously? Mike, you just said that we could only do grams and moles. How can I convert percents? Okay, I would argue it's a bad question, number one. They should be a little bit more explicit and clear with what their percent means. Okay? But if we consider kind of what we're measuring, what do we think that percent unit-wise is going to be? What phase is iron? A solid. How do we measure solids? By mass. So what's our unit going to be? Grams. So if it goes through and says that we have 22.27% oxygen, right, what does that mean? This means if I have 22.27 grams of oxygen, how many grams of the iron oxide, our starting compounds, do we have? Yeah, 100 grams of our iron XOY. We don't know what the X and O and Y are. Right? That's what that tells us. Right? We only have iron and oxygen, right? So what if I just have, I don't know, let's just say for giggles, 100 gram sample. How many grams of that would be oxygen?
22.27.
Cool. So if I just say 100 gram sample, that means I'm going to have 22.27 grams of oxygen. And in the empirical formula, we can't use grams, so what are we going to have to convert to? Molecules or moles? Do you want to convert grams into molecules? Yeah, hopefully no. That's a painful calculation to deal with. But if I go grams into moles, is that a straightforward calculation? Yeah, that comes straight off the periodic table. 16 grams of oxygen is 1 mole of oxygen. I can go through and I get a number here of 1 point. Oh, I don't know what that did. 0.5? 0.4. I'm not a human calculator. 1.39. Yeah, it's exactly what I said. 1.39 moles of oxygen. So ta-da, I know my chemical formula then. Oh, why do I not know my formula?
You would figure for iron.
Ah, dang, but I don't know anything about the iron.
Yeah, you do.
What do I know about the iron?
If 22.27 grams out of 100 is the oxygen, then what, 77.73?
How'd you get
is
that?
iron. You subtract it.
There's only 2 things in it. The remaining mass must be the iron. So I'll go 100. We'll switch colors because it's iron. 100 gram sample minus the 22.27 grams of oxygen is going to, what did you say the number was? 77.73 77.73 must be grams of iron. There's only 2 things there. And if that's in grams, I can't use grams in an empirical formula. What do I need? I need moles. How do I convert the grams into moles? I go back to the periodic table and iron was 55. Cool, look at that. 55. Whoops. Make sure you write it with the proper unit. It's 55.85 grams is 1 mole. Human calculator, beep, beep, boop, boop, beep, beep, boop, boop, beep, beep, beep. 1.41. See, I did such a good job. Moles of iron. So now my empirical formula must be Fe 1.41 1.39. Ah, dang, but that doesn't fit the proper system that we just talked about. I need to be able to use moles or molecules. I can't use molecules because that's fractional. So what do I have to do? How do I convert those numbers into a whole number? Divide by the smallest whole number, our 1.39. We're going to get Fe equals 1.001 something or other. The oxygen will be 1. Now we can follow your track and we can round. And we've got Fe101, also known as Mike. Anybody speak Spanish? It's a joke. One person got it. That's all that matters. We good? No, that's fine. Okay. The whole process of our formulas is how do we get it into moles and then realize that we also have to have our formula deal with molecules, so we do a reduced ratio to get it down into that molecule system. That's the point. Really, no one speaks Spanish.
Okay.
Fudge knuckles. It was fun. You read back and listen to what I said when I mentioned we got Mike as the answer.
I just didn't have like the context, but I get you now. I get you now.
My jokes always get funnier when I have to explain them.
You try, you try.
Hi, we good? No? Why no?
You just gave a face, I can just tell.
Okay. Cool, we got an expert at reading me. That's it. There's nothing else to say. That's the answer. We're done.
So it does have to be an exact ratio.
So the ratio comes close, okay, and it should be rounding close. 1.58 is not close to 2. Okay? Which is what our other answer came out to be. Okay? So there will be potentially cases where you come up to something that's like 1.5. Well, how could that possibly be the case? So can I erase all this? Should I erase it all and then erase it all? So let's say we went through and did a calculation with iron, and we get the answer Fe1 O 1.33. I may not have done the math right, but we'll see what happens. I don't think I did the math right.
So then you would just have to round down, right? Because you can't have like.
1.33 is a big jump. So the only case where you would round down would be a situation in the lab where you're forced to, and ultimately if you got a number like that in a lab calculation, you screwed something up royally, you would double back and you would try the experiment again, okay, to verify that you're getting a ratio like that. Yeah, I totally screwed this formula up. What is 1.33 in a fraction?
4/3.
Cool, 4/3. So if you got a system like that, how can we get rid of that fraction of the thirds? Multiply by 3, then it cancels. But if I multiply that by 3, what else do I have to multiply 3? So I would get Fe3O4. So you can get weird ratios where the numbers coming out fall on these kind of weird fractions. Usually when we talk about Chem 130, they fall on a more obvious fraction, not on a third, but on a half. So you would get 1.5. Okay? In fact, that's actually the one I should have done. Okay? We had this and 1.5. Well, what is 1.5? 3 halves. 1.5 doesn't allow me to round to 1 or 2. I'm in the middle. All right, so how do I get rid of the 2? Multiply everything by 2. So I get Fe2O3. That becomes my empirical formula. That's a painful one to have to deal with because sometimes it makes sense and sometimes it doesn't to do that multiplier. Generally speaking, the multiplier system works horribly for lab and it works beautifully for lecture because in lecture we give you perfect results, whereas lab you get your results, and since you've never done it before, your results are going to be trash. Kind of, sort of?
So is this the answer or is the last?
What did we just do for this one? How did we generate this?
You multiply?
Why did I multiply it? Where did I get the numbers? Fe1, O, 3 halves. If you go back through the video, we entirely made up these numbers. So the answer to the previous question, what did we decide the answer was? It was FEO. Okay. What we shifted to was what happens if we get numbers that aren't perfect, that aren't super close. So we needed an example of what it would mean to be not perfect, and there's no way in hell I'm pulling out percentages to get it that close to being a not perfect. Kind of makes sense? So is that all we can do with empirical formulas? God, I hope so. Ooh. Ta-da. Oh, it legit it died. And the active, it's now saying how do we get the molecular compound or the molecular formula. Right? Couple different approaches to this. if we looked at an empirical formula, that was CH, right? The molecular is now some scale up of that. Okay, so what are possible molecular compounds? CHOOH is now bringing in oxygen. According to the empirical formula, do I have oxygen? Nope, so no oxygen. C2H2. That's a scale up. And the scale up is matching the perfect ratio, because remember, the empirical is your minimal ratio. So C2H2 is perfectly valid. C3H3 also works. So does C4H4. So does C20H20. So does C1000H1000. All of those maintain that ratio. Okay? So they're all scale-ups of the empirical formula, our reduced ratio. Which one is correct? Okay, so there's a couple different approaches behind it. Okay, I would argue one very valid, logical way to go through and do this is really just a guess and check. Okay. The first part being you do have to recognize that what your valid empirical formulas are, or your valid molecular formulas are. Okay, but then after that, it says the molar mass is 78.1 grams per mole. What things are contributing to that 78.1 grams per mole? Only carbon and hydrogen. How much does carbon weigh? 12. How much does hydrogen weigh? 1, more or less. Okay? So if I looked at the empirical formula, its molar mass would be the sum of 1 carbon and 1 hydrogen. So that would be 13 grams per mole. Is 13 grams per mole 78.1 grams? No. Okay. How about the next one? Well, I have 2 carbons. Okay, and 2 hydrogens. So I can go through and do all that math or realize what did I do to go from CH to C2H2. Multiplied by 2. So my math is 26 grams per mole. Is 26 equal to 78? No. So then what do I do? 13 times 3. 36? 39. Okay. I was not actually going to volunteer a number because I didn't know what it was. So I'm right there with you. Okay. That's still not right. So what's C4? 52. Still not right. What's C20? C20 is 2. Did you really just do that?
It's just 13. Wait, that might be wrong, but
No, you're getting a lot of people also saying it. Wow, okay, good job, guys. Congratulations. That was fantastic. 260. So we way overshot it. Okay. So maybe going to 20 was a bit of an exaggeration, and maybe we shouldn't have gone to 20. Maybe we should have just added, I don't know, one more, and we get.
65.
Okay, I lied. 2 more. 78.1. So what's my empirical formula? C6H6. Okay. This, I would argue, is what I would call brute force. We just smashed at it and hoped we eventually got there. Perfectly acceptable. It works because your brute force, you're not going to go up to 200. You're not going to go up to thousands. Okay. You're going to be less than 10. The amount of times that you would have to mash numbers into the calculator is relatively minimal. You could just pull this off. Okay. The more elegant fashion, if we know the final mass is 78, okay, for our molecular, we'll call that our molecular mass. What happens if we divide by 13? Well, what was the 13? The empirical mass. If we do that division, what we're going to get is the ratio. The ratio that we scaled it up by. 78 divided by 13 is 6. By doing that one calculation, I now know my answer is C6H6. Okay? Both methods equally acceptable. This one I would argue is what I like to call sometimes is an elegant solve. Okay? That's typically how it's presented in a textbook. Okay? And then the other method that we've got over here would be kind of a brute force we just tested. The only reason we can go through and just test it is because we have multiple choice answers. Okay? What if your instructor thought that this was such an important topic that it shouldn't be multiple choice and it should be show your work? You could still brute force it. You just show all that work that we just wrote out. Okay? That's still perfectly acceptable. Right? Someone might go through and put an ugly or smiley face, unsmiley face. What's the unsmiley? Frowny face. Okay, next to it and being like, that's not very nice. Why'd you do this? You could have done it like this. And then you'd be like, screw off. I don't care. I'm done with chemistry. Okay. I'll just cry myself to sleep. Right? I wouldn't because I think it's dumb. Does that make sense? So your empirical formula fundamentals, it's getting moles or molecules. That's the two pieces that you have to acknowledge. Your empirical formula, the numbers have to represent your number of moles, okay, and simultaneously also be able to represent the number of molecules, which means you need the smallest whole number ratio. The molecular formula is some scale up of your empirical formula, and that's it.
Okay, so with this, because the carbon hydrogen is like a 1:1 ratio, so if it wasn't a 1:1, then like the 6, like what would that, what function, what would that do to? You know what I'm saying? Could you just count it by?
So let's say your formula was C1H2. You make me do math. Suck at math. So just help me out with this. I need 6 times 12, what, 72? Okay. And I lied. I need 7 times 12, so 84, right? Did I do that?
Yeah.
Okay. So our molecular mass is 84. Okay, so I believe this satisfies your question because now it's not both 1-to-1, right? How does this go through and change our approach? Well, what are our possible molecular formulas? Brute force, C2H, C3H, right? So I need to stop writing and trying to talk to you. But like you can see how you can still build out the same system. You can still go through and check all of those. Okay? The elegant method, we know the molecular formula is 84. What's our empirical mass? How'd you get 14? Whoever said that.
And your grams for the carbon and then like the 2 hydrogens.
From the periodic table, the mass of carbon is 12. The mass of the hydrogens, each of them was 1. So for C1H12 is 14. So what do? I take 84 and I divide it by 14, and hopefully I get 6. Okay, so now what does that mean? That was my scale-up factor. Okay, so I'm going to scale up the 1 by 6. How do I scale up 1 by 6? It becomes C6. How do I scale up the 2 by 6? Does that work? So it doesn't matter if it's 1-to-1 or anything else. What's going to change is how you're getting that empirical molar mass. That empirical molar mass should be relatively straightforward. It's one of those kind of things that you're just like, how do I do that? You know that elements that make it up just pull their masses in. Does that help? And it can be made more complex. You could have carbon, hydrogen, and oxygen. You could have carbon, hydrogen, oxygen, and nitrogen. Your process is still going to be the same all the way through. And I was initially going to do something with oxygen. There's no way I was holding those numbers in my head. Okay? Other questions? Okay, and all our other systems will note that we still follow the same patterns. I would argue this is a case where I'm going to start to break that pattern. I'm going to try my best to mimic it as much as possible. Okay, so when we talk through our initial systems, we want to identify what we're solving for, what quantity in moles of chlorine. Okay, so we know we need to solve for the moles of chlorine. So I would write that out, moles of Cl2. Okay. And then I would write down my given information. Gas, I have a temperature of 120.0 degrees Celsius. I have 33 ATM. What does ATM stand for? Atmospheres, which represents pressure. And I have a vessel of 12.0 liters. What is liters a measure of? Volume. Okay, so my volume equals 12.0 liters. Could even get, and here's where I would start to modify a little bit. I was being asked for moles. As soon as I'm seeing temperature, pressure, and volume, I'm immediately going to have something trigger in the back of my head that says that moles, I'm actually solving for N, the number of moles. Okay? Why do I have that triggering in the back of my head? Pivnert. So now I would effectively ignore that I wrote that, and I would write PV equals nRT. Okay? P is pressure. T, I don't know how I'm doing T. V is volume. N was our moles. R we'll come back to. T is temperature. Okay? This is an equation that I could now manipulate and change. If I want to solve for the moles, I have to then say N equals PV over RT. Okay, do I know P? Do I know V?
Yes.
Do I know T?
Yes.
What the hell is R? R is the gas constant. It's what makes this equation actually valuable and useful. And so that would be something that if I were a student, I would send an email to my instructor to be like, do I need to memorize what this numerical value is, or are you going to give it to me? And mainly you need to email me because I've already forgotten to check. Okay? So someone should email me to verify. I think it's something I would give you, but I'm not 100%. Okay? For the sake of this question, you would have to acknowledge it's a constant, and you would have to go and look it up. And R is 0.0. This is one of the reasons why I need to give it to you. Is it 2 zeros? 1 0. 8.2. And then for one stupid reason, I know the rest of the numbers. I just don't know how many zeros go in front of it. Well, zeros don't matter, right? It's a joke. Officially, the unit's liters, atmospheres per mole times kelvins. Okay? And I helped someone with this in the tutoring center, and they got really bogged down by the massive amount of units in that R system, and they get really confused. Okay? The whole point of R with all those massive units is that what happens? This equation works. Okay? So here's the massive shift. When you're dealing with Pivnert and gas stuff, memorize a formula. And you're done. Because now all you got to do is sub the numbers in. Okay? There are some subtle things that we do have to watch out for that we'll address here. Okay? The units do have to match from your R. Typically, we represent pressure in atmospheres. If you have to move into 151, they may not give you atmospheres. In fact, I've seen other 130 classes use units other than atmospheres, and it confuses me. Okay? I don't know why we would do that to 130 students. Okay? Volume should be in liters. Typically, when we're talking about gases, they're in liters. So it's very rare to see any other measurement other than liters there also. Okay? Moles is a standard unit that always shows up. And then that last one, K, becomes important. That's the real kicker on this one. K is Kelvin. Typically, when we measure our temperatures, we aren't measuring in Kelvin, we're measuring in degrees Celsius. So you do need to know the conversion between Celsius and Kelvin, and that means you have to add 273. That's all you really need to know. If you want to get fancy, you can add the 1.5. Okay? So when you go through to solve this, that temperature has to be 120 plus 273. At that point, it's now just plug it all in and solve. Does that answer your question? Ish?
So, so when you plug it in, it would be the P times the volume.
So I would get 33.3 atmospheres times my volume, 12.0 liters. This is where it's going to get ugly. Divided by 0.082115 liters times atmospheres divided by moles times Kelvin. What color did I pick for temperature? Purple. Can someone give me a number? 120 plus 273? I heard 330? 393 Kelvin. Okay, so personally what I would do is take the 33.3 times 12 and I would write down that number. I would take the 0.082115 thing, okay, and then times the 393, and then I would write down that number. And then I would take my brown number and divide it by my dark purple number. Okay? And you're like, well, what about all the units? You always care about units. I do always care about units, but this is gases and I don't know. Okay? Do the gases or do the units all do what we want them to do? Actually, yeah. Or atmospheres is in the numerator. Atmospheres is also in the denominator. So those units cancel. Liters is in the numerator, denominator. Then you go, well, Kelvin is in the denominator. True, but it's also in the denominator's denominator, which means that can cancel. Okay? And then this is where it gets a little bit weird, kind of unit-wise, and this tends to freak people out a little bit, which is why I would say you just plug it into the calculator and be done with it. Okay? Our unit at this point would be 1 over moles, which is a really goofy looking unit, but what does that ultimately equal? Moles. Okay, and the example that I usually pick to help highlight that, because that kind of helps, is let's take 1 over 2. So another way, let's take 1 and divide it by 0.5. And guess what you get? 2. Okay? So mathematically, dividing by a fraction is the same thing as the super denominator, if you want to call it that. Okay? And there's other things you can do mathematically to play with that unit. I would argue it's not worth your time to mess with it to actually be able to see that system. All you really need to know is formula works. You just have to plug in those numbers. So if you've ever complained and been like, but I want a formula. Dude, I'm giving you a formula. Stop complaining.
So what do you put for units?
Sorry.
So I'm sorry, back to the dark number. To get the dark red color.
33.3 times 12 gets me this number. Does somebody have a calculator?
399.6.
Really? Okay. Uh, 0.08. Now, black times purple.
32.2712.
32.2712. Okay. I'm going to be sick of writing that out, sig figs wise.
399.9 on the top number.
We'll just fix it for everybody. So you should take 399 divided by 32.27, and you get 12.38.
299.6 is right.
You should get 12.3826 moles. Okay? That's what it comes out to be. Okay? For the record, I was being kind of creative, right? What's red plus green, color-wise? If you mix red with green, you get brown. And if you mix black with purple, you get dark purple. Look at that, color coding. Okay, does that help?
Oh, yeah, makes sense.
To the units of moles, it just comes out to be moles. Okay, so that I would argue you don't need to track the moles. All of that, as long as you're matching the units, as long as pressure is atmospheres, volume is liters, temperature is kelvins, it works. It's going to get you the unit that you want. Okay, so that can be the nice thing in that system.
So are you giving us the R?
That's the thing you have to send me an email about that I have to go and check and verify that's on the front of the exam. I would cautiously say yes. Mostly because I don't have it memorized. And if I don't have it memorized, generally speaking, I should allow you to have it.
Okay.
Make sense? Okay. Everybody's getting excited and packing up. We do officially have 3 minutes, so if you have more questions, we can do that. If you don't have more questions, you can hold those questions for Monday. And then our quiz is next Wednesday, now that we've had some time to check and verify the calendar, because clearly I can't do that very well. And so, yeah, Monday is, again, another set of review, right, working through questions. If you don't have questions, I'll try and make up some of my own to throw at you. And generally speaking, people don't like that. So come with questions.